All right, welcome everybody to the last week of school, week 18, day 1. It's IS50B. We only meet once a week. So today we're going to be talking about the bounding volume hierarchy system. And this is a very, very common way for worlds in video games to be held. It's a data structure that is, it can be done in a number of different ways. In this case, it looks like they're doing it as a binary tree. I don't think it has to be a binary tree, though. And so have you guys heard of like RTX on? Like, have you guys seen those memes? Like there's these kinds of memes of like RTX on, RTX off, RTX on, kinds of things. So, have you ever wondered how? That's so disturbing. Have you ever wondered what that actually means? Like, what is RTX? Unsea juice. It's funny. Like, how does that work? How do you hardware accelerate ray tracing? You know what I mean? So like ray tracing is the notion that for every pixel on the screen, you're going to send one, or in reality more than one, a photon out of your eyeball, right? And so if you've got, that's actually how the Greeks thought that your eyes worked. They actually thought light came out of your eyes, and then they reflected off the mirror and see something. So like if there's a mirror, and basically I'm shooting light beams out of my eyes, and you see the thing, but if it's dark, then I can't see anything. So they had the kind of causation backwards, but that's actually how ray tracing works in video games, right? So if you have some scene like this, the normal pipeline for doing graphics rendering is rasterization, triangle rasterization.
Comes out of your eyes.
Yeah, well, there's two different things. There's triangle rasterization, which is your typical non-RTX way of doing video games that we've been doing for 30 years. And then there's the RTX, the ray tracing way. Okay, so the old way, you would have triangles. You'd have a bunch of triangles on the screen, and you rasterize them. To rasterize a triangle is you take the triangle and you draw, there's like a 2D image buffer, and you write the colors for that triangle into the image buffer, as well as how far away it is. And so if something comes in front of it, then the nearer pixels get drawn over it, and if there's something in front of that, that gets drawn in front as well. And so your performance will actually degrade quite severely if you've got areas where there's a lot of overdraw. If there's a lot of places where the triangles are blocking triangles, it's just going to draw all the triangles over and over again to the same spot. And your fill rate, which is how many billions of pixels per second your video card can draw into a 2D array like this, it'll hit a limit and your frame rate will start tanking. Now, ray tracing is often said to be a slower method of drawing a picture to a screen, right? You guys have all heard this, right? Like you can do it with triangles or you can do it with ray tracing, but ray tracing is really slow. Have you guys heard this kind of notion before? Have you guys heard that? Like, ray tracing is just slower than traditional rendering? No? Never heard that before? Ray tracing has traditionally been used in like Pixar. Right.
What's
so
ray tracing?
Ray tracing is, that's cool. Oh, neat. Yeah. So in cars, how they I'm gonna download that actually. Save that. Computer science papers. Render man, and we will not care about it for now. Anyway, so traditionally movies and things like that have been ray traced, and so what they do is like let's say you have a picture like this. This is from Pixar. So let's say you have a picture like this. Okay, and so what they'll do is they'll set up a single frame of a movie. And then they'll say, render it. And then Pixar has this giant render farm. And they have all these computers. And basically what they do is over and over again, they send photons out from every pixel on the screen. They send a photon out. And the photon travels through the world. It's like glass. Okay, cool. Glass. Now it splits the photon. One of the photons that gets split off refracts, and one of it reflects. Ada, do you know what the difference between refraction and reflection is?
Yes.
What is the difference between refraction and reflection?
Refraction directly copies an object, while refraction, it's like if you put a straw into water, the image will appear separately.
Okay.
Or
and then
it'll appear differently.
And then what is reflection?
Reflection is when the picture of an object bounces off another surface.
Correct. Yeah, so for every surface like this, you can see this is reflection here. And then the refraction, you see the refraction here? Like the green, you can see through this glass dragon here. So when the light enters the glass, it bends, that's refraction. And so every time you hit a glass surface, you send off 2 photons, one for refraction, one for reflection. And there's a percentage that each of those photons will contribute to the final image. Might be 50-50, might not be. And it takes a day to render a second, something like that. Yeah, something like that. They have a huge compute farm. And basically, the artists will basically work during the day, and they're like, render. And then they go home, and then when they come back, this compute farm...
Are you going to eat? That's why I brought you your burrito.
Well, I can't eat while I'm talking, girl.
Then why did you ask me to bring it?
Well, I was expecting some of my students to present today, but I don't know if any of them are ready. Maybe not. So anyhow, they send billions and billions of photons, and then they average the results together, and they can get really nice, really photorealistic looking images as a result. Now, what does that have to do with RTX, and what does that have to do with data structures? Because we have a bunch of CSI 41 students here today. How does that relate? Well, what is RTX? How do you hardware accelerate this? Does it just do the lights? But how does the graphics card even know what the world is, and what's in the world, and what's glass, and what's reflective, and how does anything get shared between the programmer who is making a world and the graphics card, which wants to hardware accelerate ray tracing
what I tried asking
in this world?
That's, I guess, what I was trying to ask you a while ago. I guess I'm going to get some answers.
Okay, good. Mulia was asking about it too. How does the
you said that they you said that they punch holes into a paper, but how does it detect even that? How did it all start out?
Right, so there is a person, like the artist who makes this, or the video game person who makes it, and they make a data structure. They make a data structure called a Bdh. And that data structure is then passed to the graphics hardware, and the graphics hardware accelerates the Bdh tree, essentially. So you construct a data structure, you share it with the graphics card, and then the graphics card, which is a massively, massively strong device, right? Your GPU is far faster than your CPU. NVIDIA 3090 flops. No, not flops. Flops. How many floating point operations per second can this thing do? NVLink. All right. So that's pretty good. Okay, I don't know what this number is. GPU. 30 integer operations per second. Does it have actual numbers? There we go. How many teraflops is in RTX 3090? All right. It's clock speed, core count times 2.
There's 36 in that comment.
Does it say 36? Okay.
Yeah.
Yeah. So it's beefy. What did you say? 36 teraflops? Yeah. 36 teraflops. Okay. So my Core i9 7900X flops. how many floating point operations per second can this bad boy do? Flops. It's not on the page. Why would you turn that up then?
Computers have genders.
It's a phrase, girl. It's a phrase. Best around, yeah. It's. Can you find that for me, will you? Do we have any flops on here? Anyone? See, I don't know why it's like turning up these things that don't actually have the keyword that I'm searching for. Now, let's see if Google can do better than DuckDuckGo. i9 7900X flops. 638 gigaflops. Okay, so times 10 times 5. So my video card is 50 times stronger than my CPU. Okay, so that's assuming that I'm using all 10 cores on my CPU, which can cause heat issues because it burns a lot of wattage. So I have a fairly decent CPU, and yet my GPU is 50 times faster. Okay, and so you really want to be able to offload things onto the graphics card as much as possible. What do you want to accelerate? We want to accelerate, can I shoot a ray out of the camera and you tell me what it hits? Okay, and so by putting this data structure onto the graphics card, you can make it so that you can accelerate that trace line, that ability to, for this pixel right here, shoot a beam of light out of my eye. It hits the blue surface. It reflects off. It does a shadow ray to see if it can see the sun. We want to accelerate that as much as possible. Then we can throw more and more photons at this world, and the more photons we throw, the better the quality looks. All right. So if we see what the goo.com like Battlefield RTX quality. If we look at what the different quality settings make, it's basically how many rays per second you're sending. So let's pull this up here and real-time ray tracing. Let's do side by side. There we go. Zoom in. Thank you. Okay. So over here is low, medium, high, and ultra. And here you can see like some of the fire has vanished. I don't know. I honestly can't really see that big a difference here. I don't know.
Raytracing is much better when you're actually looking at like just water.
Yeah.
Like if you scroll up, there's a picture of like the water.
Yeah, but there's no side by side comparison. I've actually played that level, and there we go. All right, that's better. Yeah, so you can see that like when rays hit the thing here, you get kind of a low quality image. And what is that? Off. Okay, that's off. Then low, and then high. And so the more pixels you throw, the better the rendering quality you get. Okay. And yeah, you can see here off, like there's no decals on the thing. Probably the shadows are going to look a little better too. Yeah, you can see the quality of the shadows up here. Look a little nicer. Yeah, it's mostly water and reflections look better. And then you can see the difference in rendering time, right? So with ray tracing off, you get 150 frames a second. With ray tracing on low, you lose half your frames per second, which is brutal. And then you put on ultra, it actually doesn't dip too much more beyond that, but still 50 is kind of painful. Then on higher resolutions, you have to send more pixels out. So, what, 2080? Yeah, okay. And so you can see there's a cost to ray tracing, right? But here's the kicker, and for those of you that are waiting for me to get into the data structure, I'll do it in a second. The thing about this is that if you ray trace, it actually doesn't matter really how many triangles you have in the world, right? Because that overdraw problem doesn't exist, because I don't have to draw every triangle over and over again. Like each one of these blocks here is probably going to result in drawing that block to the frame buffer. It's going to draw to the screen. The screen is just like a 2D image, red, green, blue, and depth, and alpha, transparency. And so each one of these squares in Minecraft is going to draw, under a normal render, it's going to draw over and over again. So all of these spots here are going to be overdraw over and over again, unless the engine does something clever to determine when something's not visible or something like that. With ray tracing, though, you don't have that problem. So in theory, ray tracing can be faster. So even though we just saw that ray tracing has a 50% speed penalty, in theory, ray tracing can be faster. It really depends just on the world you're trying to draw. And in theory, the quality of ray traced images is better because you're actually directly simulating light traveling through the world and bouncing off things and refracting and things like that you can't really do with triangle rasterization, right? When you're drawing a triangle here, you don't really know where the light's going to bounce off of it, right? And so they'll do things like when they have a water thing like this, they'll just sort of simulate it, and it oftentimes looks bad and things like that. But with RTX, you're actually directly simulating photons and things like that. So in theory, ray tracing can actually be faster. And so how do we do it? What's the secret sauce here? Well, the secret sauce is something called Bdh. And this is the most common data structure used. It's, I think, mandated by NVIDIA if you want to accelerate your ray tracing. There's also something called an octree or quad tree, which is also fairly commonly used in graphics programming. I used quad trees and octrees a lot in my master's thesis. And so basically it's a binary tree, except it's got 4 subtrees. And so the root is here, and then it's got 4 kids, top left, top right, bottom left, bottom right. And then if there's anything in that, you subdivide, and you subdivide, and you subdivide, and you subdivide recursively until every square has at most 1 node in it, right? And so areas that don't have anything in it require very little storage to store. Areas that are very dense have a lot of data in it, and these are used for all sorts of different purposes. And they give you kind of a spatial representation of a world. And octrees are just the 3D equivalent of that. So an octree would look like this. And where you divide the world into 8 subkids, and you keep subdividing and subdividing and subdividing until every subdivision, every node on the tree has at most 1 object in it. Okay, and this is very, very commonly used. It's been used in graphics for what did that just say? 40 years, something like that. So what is a Bdh? Okay, so Bdh. There's a couple different ways you can do a Bdh, but basically you can think of it AABB, axis aligned bounding boxes. Yeah, let's show that. So let's say that you've got a bunch of shapes in the world, and you're gonna do some ray tracing up in here. Can we not have it be transparent? Maybe, yeah, that'll work. Goodness, why do they use SVG? It's such a weird thing to do. Okay. So I'll just paste it in here. This will work. Okay. So let's say this is your world. This is your world. Okay. And let's say the user is one node. Why are you so terrible? There we go. All right. So let's say the user is here, and they're going to be shooting. They've got a field of view that's like 90 degrees, like this. And so what they're going to do is for every pixel on the screen, they're going to shoot a ray out. Okay. And with and you've passed on this bounding volume hierarchy to the hardware. The hardware can accelerate this very, very quickly. Okay, so let's take this ray here, for example. Is this ray going to hit any of the objects in the world? What do you guys think? Is that ray here? Like, remember, for ray tracing, what you do is for every pixel on the screen, you shoot out a photon. And if it doesn't hit anything, you're done. That's easy. You don't have to send out more. You're done. Enhancing photorealism, enhancing. Oh yeah, I've seen that. Yeah, the Grand Theft Auto thing. Yeah, that's cool. So this ray is not going to hit anything. Okay. Now, how do we know this using a data structure? Well, all of the objects in this world are enclosed within what's called a bounding volume. A bounding volume. In this case, it's just a bounding box. In this case, it's actually what's called an axis-aligned bounding box, AABB. Right? So this is going to be from x is equal to 10 to x is equal to 30, from y is equal to, I don't know, 100 to, I don't know, y is equal to 400. That's everything in the world is within this bounding box. And so how can you mathematically tell if this ray is going to hit this bounding box here? Guys, have you ever done the line intercept algorithm kind of thing? Y is equal to mx plus b. You guys remember that? So we'll just do 2D because all 2D things can usually be extended to 3D pretty easily. So let's say that we've got, just to make life simple here, let's say that y is equal, for this ray right here, we're just going to say y is equal to, the slope would be 0, I guess it's horizontal, 0 times x plus, I don't know, 500. Okay, so we've got this line coming in here, y at 500, flat. How can we tell if this line here hits any of these objects in the world? Right? We could, and this is kind of annoying too, right? Like these are, you know, you can have all sorts of like weird shapes, you know, and stuff like that. You know, how do we know if this line hits any of these guys? All right? Well, we have a data structure. We have a data structure called a bounding volume hierarchy. Okay? And this is a very simple bounding volume hierarchy. In reality, you would have subnodes maybe like this, like this, like this, like this. Okay. And so the root of this is a tree, right? And so the root of the tree is the big boy box, and then the big boy box, which is this whole thing here, and it's going to write down from x equals 10 to x equals 30, and from y equals 100 to y equals 400. That's all you have to hold. So when you have an axis-aligned bounding box, it's very simple. All right, minimum x, maximum x, minimum y, maximum y. That's it. Or you could hold down like x minimum and the size, which works out to be the same thing.
Bless you. Bless you.
Okay, so how can we tell if a line crosses a box? Well, one way we can do it is we can plug in x is equal to 10. Because here's an observation. If we have a line crossing a box, no matter how we draw it, it's going to cross the line in two places. It's going to cross it once on a horizontal, you know what I mean? Like it's going to cross in two places, right? And so technically you don't need to check all four equations. You know what I mean? If you just check 3 of them, it should be good enough. I don't know if that matters. So what you can do is you can just plug in x is equal to 10, right? So you take x is equal to 10 and you plug it into the equation of the photon we're looking at here. 10 times 0 is 0, plus 500 is 500. And so that tells you where the photon crosses the box on the left edge. Do you guys see that? You take the left edge is 10 here. That's x is equal to 10. So you take 10, plug it into the equation, and you get where the photon crosses the box at the left edge. It's 500. Is 500 greater than 400? Yes, we missed. Okay. Then you repeat for each of the other lines. It's pretty simple. You only have to do 3 of them technically. And so like, did we hit the right edge over here? We plug in 30, we still get 500. 500 is bigger than 400, so we missed, right? And yeah, and so that's basically it. You just do a line intercept by just taking the number, plugging it in, see if it's within. So you take the x value here, and you see if the result is between the min y and the max y. Okay. We got a miss. We're done. That's it. We're done. So if we have a miss, we don't have to worry about that photon anymore, right? So that photon is not going to hit any of this stuff. All right, we got all this stuff inside of here, and we shot out a photon down here somewhere. It missed it. Nothing. Nothing in the world we're going to hit. So you just return miss. And so that photon is going to report back, I missed. I didn't hit anything in the world. And then the renderer will be like, all right, if you don't hit anything, draw gray or green or something. You know, there's some default color, black maybe. Blessed be the nose that has sneezed. Do you guys understand? I know it's algebra, but it's pretty easy algebra. Like, I hope, right? The line intercept formula. When you have an axis-aligned bounding box, like the slope on all of these lines are just flat, right? So it's really easy. Just plug in one of the values and you check to see if the result is, you know, when y is equal to 100, it'll give you, in this case, x is equal to, I don't know, 15 or something. 15 is between 10 and 30. Hit. You know what I mean? That's it. Algebra. Prado, is this cool? Like, do you understand like how to do the intersection of a line with a box? Logan's here. Walker, you with me on this? So you just plug in y is equal to 400 and you get, okay, we get x is equal to 11 here. 11's between 10 and 30. We hit. Yes? No? Seaside 41 people, are you with me? Like, I know it's algebra, but like it's about as easy as algebra gets, I think. Eichmann, Arias, Gonzalez, you guys feel me on this? Like, all we're doing is checking to see if a line is hitting the outermost rectangle. Okay. So, what if we hit? Like, if we miss, easy.
That's algebra?
This
Wait, I thought algebra was just like doing math with a missing number.
Math with a missing number, exactly. And so we're trying to...
Missing shape?
Algebra can be drawn geometrically and with lines and things like that, yeah. So this data structure here is actually on the graphics card, and the graphics card can do this math very quickly. You've got a 900 trillion billion teraflop graphics card. It can do this algebra very, very quickly. Okay, now let's say that it hits. Let's say that it hits. Now that still doesn't mean that we're actually going to hit an object in the world. You know, like if I shoot a ray. If I shoot a ray up this way, it's going to intersect the bounding box, but it doesn't actually hit any objects. And so I need to go down a level. And this is where I think it's interesting for the data structure people, right? So for the data structure people, this must be inside. I shouldn't draw it with it sticking out that way. Come on. Let me erase it, please. Just let me erase. Come on, erase. Erase one note. One note. So terrible. Why are you so terrible? Okay, now we're erasing. All right, here we go. There we go. All right, and then nope. Now I want to select you. It's double clicking. It's registering the keystroke or the mouse click. It's just not selecting it. What a fantastic product this is. Like if I double click, like it pops up. It just won't select the pin. Okay, so oh my gosh. All right, let me relaunch OneNote. It's such a garbage product. Like the most basic functionality, like just let me pick a pin. It doesn't work. Over and over again. It doesn't work. All right, there we go. So the BVH will be pre-constructed by some fashion. How we make it doesn't really matter for us here. But let's say we've got this. Essentially, you can just kind of make it where you just say, what is the...
Dad?
minimum point of anything in here.
Dad?
Should include that a little bit. Yes, girl.
What day is Camilla's birthday?
It's the last Saturday, 30th. Yeah, Sunday. Last Sunday. It's May 30th.
Should you be babysitting me on that day?
Maybe. Yeah. Next extra credit is making one note. Yeah. Okay. So anyway, so we've got this this outer box. Now we're gonna have 4 kids in this case. I'm not doing it as a binary tree. I'm just gonna say whatever. So we're gonna have kid A, kid B, kid C, and kid D. Okay. And so it's the big boy box. I'm going to draw this down a little bit. It's got kid A and kid B and kid C and kid D. Now, basically, we're going to have to do this line intersection test 4 times, right? Because we got 4 kids. Because if we've entered this box, we could feasibly be hitting any of these guys, right? And I might want to subdivide it into like a left half and a right half. And if I do it exactly as left half and exactly as right half, then I've got a quad tree, essentially, right? Or a binary space partition, right? Where you divide it into half and half and divide it into half and half. And in this case, though, we got 4 rectangles inside of here. So we're going to do this line intersection test with A, with B, with C, with D, and miss, 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 hit. Okay. So now we need to go inside of A. Right, and so A might have 2 bounding volume hierarchies, 2 bounding boxes, axis line bounding boxes, one for, we'll call this guy A1, like the steak sauce, and we'll call this one A2, like not the steak sauce. And so...
so it's the sauce you put on your steak
that's
at
right.
a restaurant?
That's right, yeah, I don't know why, I don't really like the taste of A1 steak sauce, but some people do. And so...
And you like well done.
I like well done steak. I'm just gonna say it. I don't care. I like my meat to be cooked. I'm a civilized person. So weirdo. I know.
Why are you saying that? Why are your students saying that?
It's considered culture to eat your meat uncooked like a caveman. Except even cavemen cook their meat. Medium rare. Yeah. I don't know. I don't get it. Like humans cook food for a reason. So
we can burn the parasites in them.
Yeah, exactly. It's healthier. So anyway, so when we're traversing this, and the hardware, your actual RTX hardware will do this for you. It first checks to see if the photon crosses any of the things in the big boy. If it does, then it's going to check A, B, C, and D. It hit A. So then it's going to check A1 and A2. And it hit A1. It missed A2. Okay, ignore A2. And so in this way, you can very quickly discard large chunks of the world and figure out who you're going to hit. In this case, we come inside of A1, and we actually will do a more complicated collision detection to see if the ray hit A1, because this is not an axis line bounding box. It takes a little more effort. Or you can just recursively subdivide this into more and more precise boxes, right? Like you can split this into 4 boxes and then split those into 4 boxes and create a very deep, detailed tree if you want to waste the space on it. And you can break it down until it's just a simple line, essentially, inside of each chunk, which is an easy enough computation to make. So this tree can actually become very detailed. But at the simplest level, we'll just get down to like when there's one object, and then we'll do a complicated collision test and see if we hit it. We missed, so we return miss, right? Whereas if we shoot a ray this way, then we hit B and we hit C, but B we check first because its minimum is before this one, right? And so we check B. We hit the circle, so we're gonna hit. We hit the circle, right? And so if we sent an array this way, then it would return, you hit right here. So do you guys see how this can be used to very, very quickly accelerate? And even if you had a trillion objects over here somewhere, it wouldn't matter, right? Because the only bounding volume hierarchy node that was hit was the big one here, and then the small one here. All the rest of the detail. You could have a trillion objects here inside of D, and it wouldn't really matter, right? Maybe eventually you'd run out of like memory on your hard drive to hold the tree, but at a certain level, like you can actually, you know, if you're just sending array after array over this way, all the complexity and detail, the fact that there's lots of triangles over here, it doesn't matter. It doesn't keep overdrawing them over and over again, so it actually could be quite a bit faster. And when you hit a surface, then in this case it's a circle, right? And so intersection between a line and a circle is actually really easy, right? And that will tell you the exact point that the ray hit the circle, and you can get the normal. The normal is the direction perpendicular to the surface, and so that's just the direct. You know, if you got the rate for a circle, right? You got the center point of a circle, and you got the point that you hit, and it's radius away, right? And so the normal is that direction, right? It's just, you have a point on the surface of the circle, you got the center of the circle, that's the way that's the normal, you know? And so if you want to refract, if you want to refract, then you refract a ray that way. And if you want to reflect, it just reflects around the normal that way. And the same theta coming in is the same theta coming out. And then for the refraction, you have to know what the index of refraction is for the material. If it's glass, the light will bend, you know, things like that. And so you end up having to send, if this is a glass sphere, you have to send out two rays, one for the reflection, and maybe this hits some red box over here, and then it'll add a little bit of red to the coloring here, and then maybe this hits here, and it refracts again, so it refracts a ray out this way, and it bounces internally. Maybe here, then it bounces here, then it bounces here, then it bounces here, and each one of those can throw off refracted rays, right? And so typically your engine will say, what is the maximum number of bounces you can do, right? And it's usually like, I don't know, 3, you know, maybe something like that. It depends. It really depends how accurate you want the thing to be. But basically you do like, okay, this guy will shoot over to here, and then it'll internally reflect here, and then that one will shoot out a ray over here, and then we stop, right? And so what happens at the end is that it averages these numbers together, and it averages those numbers together, and passes them back up, and it passes it back up, and it averages those numbers together, and then it returns the result. It's going to be like, all right, it's 50% red, and 50%, 50%, and 50%, and 50%. And so from all these rays that get created, they all sort of contribute a value to the final value, and you will get a nice looking image, a physically correct image. And yeah, if you want to do lighting, like let's say you have a sun over here. Yeah. If you shoot a ray over here, I'm gonna have to erase this. Do you guys understand so far? Like, does that make sense? Like, you just have basically a rectangle inside of a rectangle inside of a rectangle, right? Is that, I mean, it's not too terribly difficult, I don't think. So you've got, you know, the big boy here has got 4 kids, A, B, C, and D. And again, there's different ways you can construct these things and build them. It doesn't really matter for our purposes here. It's like a quad tree, except a quad tree is like this. A quad tree, you'd split it in half and half, right? Oh, there's something here, split it in half and half. Oh, there's something here, split it in half and half. Split it in half and half, right? And you keep doing, you know. So, BDHs are, yeah, you think of them kind of as quad trees. But they're rectangles, like they're different areas of the map that have solid stuff in them. Okay, so if we were to, for example, send a ray this way, actually, let's try and clip B a little bit here. Let's see if I can draw this. So we've got our camera down here, the person's looking up this way, and we send a ray kind of up this way. I don't want to hit it. There we go. And we hit here. Okay, so the sun is sending beams of happy yellow light down this way. This is probably going to be pretty shadowed, right? And so how do you compute shadows? How do you make it so that one object casts a shadow on another object, right? Well, ray tracing is really good for that, because what you can do is you send a beam this way, and then when you hit a surface, you send what's called a shadow ray to the nearest light or lights, right? And so you've got the sun over here, and so what you do is you send a ray up towards the sun, and you see if it hits anything. Oh, we hit something. Okay, it's in shadow. Do you guys understand? And so really simple ray tracing is actually really fast, because just for every pixel you send out a ray. Finding what you hit is basically an order log-n computation to see if you hit anything. And so basically the work you do is proportional to the number of pixels on the screen, which you got to do anyway. There's no getting around that. And so if you don't do any shadow rays or reflections or refractions, ray tracing is actually a lot faster than rasterization, because when you rasterize triangles, again, what you're doing is you're taking a triangle on the screen, and for every dot within the triangle, you have to render it, and you have to do interpolation and things like that, and you render it to the screen. And then if they draw another triangle, for every pixel within that triangle, you draw it, and you're going to overdraw these same pixels over and over again. With ray tracing, it flips it around, right? With rasterization, for every triangle, you draw the pixels. For ray tracing, for every pixel, you draw the triangles. Does that make sense? So for in normal 3D games that aren't ray traced, for every triangle, you draw all the pixels on them. For ray tracing, for every pixel, you shoot it through the world and see what's there, and you draw the triangle. And so, it can be faster. Okay, and so if you want to do lighting and things like that, then it starts getting complicated, because here's the trouble. If this guy is occluded, occluded means blocked, right? Like we hit this point on the thing here, it's blocked by the edge here, you can't see the sun. Normally it would just be like black, right? There's no light source that I can see, black, right? And that looks really bad, right? Especially since this is a glass sphere we have down here. And so all the light coming off the sun here is going to be reflecting off the glass, and so the glass is actually going to be glowing quite brightly in the sunlight as there's light kind of refracting through it. And you know, if there's a surface down here, it'll probably have a little bright sunspot as the light lenses through it and makes the you know, those sun patterns, you know, like the caustics is what they're called. And so it would be really weird if this guy was like pitch black, you know what I mean? Because you got this glowing mirror kind of surface right here. Some of the light from this should illuminate this. Do you guys understand? So how do you do that? How would you do it? How would you make this spot right here, how would you make this spot here pick up some light from all the other objects around it? Because all the other objects that are illuminated are going to be radiating light as well, right? So how do you do that? How would you do it? What do you think? Have you ever seen like a fire truck drive past a White House? The White House will actually turn red as the fire truck moves past it. All the light reflecting off the fire truck reflects onto the white surface, and like this, right? So when light bounces off a surface, it's going to light the surfaces that it hits. Yeah. So you see some of the light coming through here, and you can see the caustics underneath there. Like that was what I was talking about, which is when the light makes cool patterns going through surfaces. But you can also see that the red wall here. Let's zoom in on this. So you see how there's a red wall here, and the white wall here is picking up some of the red, and the blue wall here is kind of making this part a little bit blue. It's kind of subtle. And then you have light passing through these translucent objects here. You can see that it's passing through the green, it's passing through the blue. Obviously this is a ray traced rendering, right? And they would probably, like, if it's allowing light to go through green and blue, then probably the maximum number of reflections, and refractions is higher, right? If you're not doing video games, you can set that number up as high as you want and just let it render for a while, you know? More and more internal reflections and refractions. Go for it. The more pixels, the better. So how would you guys have this surface light this surface? Right? Because when you're rendering like this spot here, we send a pixel from the camera. Our camera is here, right? Our camera is here. And for every pixel in the world, we're shooting a photon out. So for example, when we hit this spot right here, it casts a shadow ray at the light, and it's like, oh, I'm visible, so it gets white light. And the amount of white light it gets is based on how, see, when the normal is pointed at a light, you get a lot of light. And as you tilt away from it, you get less and less light until it becomes shadowed. You see my hand here? When the normal vector is pointed at a light, you get a lot of light. It's the cosine of the angle is how it works. And so this is getting, you know, a fair bit of light here. But how do we have this work? How do you have a red surface illuminate a white surface? You know, do the same process again. Give the ray the color of the wall and shoot out more rays. Yeah, sure. Okay, so so when we hit this surface here, then the usual approach is actually just to start scattering random rays. We just pick a random direction. And again, the quality controls how many rays you send out. And so if this doesn't hit anything, nope, no lighting. This doesn't hit anything, nope, no lighting. And if that's all you did, it would be black. Sorry, sucks for you. But we're going to scatter maybe a dozen rays. You know, that might be a little high, but when we hit this point, we can scatter a dozen rays out. Oh, look, this one hit the glowing glass sphere. Okay, well, what is the brightness of this? Well, have we computed it yet? I don't know. You know, so when you hit this point needs to cast a shadow ray up to the sun and be like, oh yeah, I'm fully lit, you know? And so you can see how, like, ray tracing can become very expensive, right? Because you hit this point here, and then each of those dozen rays that come out, those guys also go out and refract and reflect X number of times, maybe 2 times, maybe 3 times, right? Depends how much fidelity you want in your image. But this guy eventually discovers, oh, look, the sun is shining very brightly on this one, and I have a clear line of sight at him, and so that is going to be, I'm going to be getting light from that. And so in this case, I sent out 1, 2, 3, 4 lights. One of them hit a very bright thing, and so I'm going to pick up 25% lighting, right? Miss, 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 and a hit on a very bright thing. So I am going to be 25% lit. And so that way, the surface down here will be lit at a nice 25% rate.
I have a question.
Yes.
When you're doing that bounce,
Mhm.
wouldn't you only need, like, depending on if the material of that box is translucent or just transparent and rough, wouldn't you only need to draw one ray on the bounce? Because it would just be like an angle of incidence equals reflection. Kind of
Because we're not reflecting light off of the sky. We're trying to see what light is hitting the sky. What light is incident upon the surface. Do you see that? And so even if this guy is fully like not translucent, no, like maybe it doesn't, you know, it's not translucent at all. We just want to, like, imagine there's a flashlight, you know, shining light on the sky, right? We need to know what light sources are hitting us. And so what it does, it will just randomly shoot rays out, and the more rays you shoot out, the better. And if you discover, oh, hey, there's this, like, the surface is exposed to the sun, the surface is very bright, and it hits that, it's like, oh, well, that light is going to be incident upon me. And you do, like, a exponential fall off, right? Because the further something is away, the less bright it is. And
I think Sam had the same idea of me. So I was thinking, like, can it just be angle of incidence reflection? But the difference there is, I can't do that, as Karen just explained, is that we're not looking at, like, what we're seeing. We're looking at how bright the box itself is going to be, and obviously where we're looking at the box is not going to impact how bright it is.
Yeah.
Unless unless they have, like, kind of, reflective surface where when you look at it, it actually does change. But that would only apply for reflection, not for coloring of the box itself.
Yeah, what we want is to know how much, because we want light to bounce around, right? And so, like, this is Quake 2 RTX, right? And so this is a very bright red surface, and so when we shoot a ray out of our eye and we hit the wall there, it's going to scatter a dozen rays in different directions, and this one hits the red, and this one hits the red, and this one hits the red, and this one doesn't, and this one hits something that's red also, so it picks up red from that. So what happens is that you actually get this nice volume fill of light kind of moving around through the world, right? And you might be like, but wait, it's random, right? Like, how do you... right, so here's a window.
Oh wait, is that randomness what causes the need for a denoiser?
Yes. Yeah, I'm about to get to that.
Oh.
So you've got here this thing, and there's no lights inside of this room, right? All of this is just natural lighting. And so the light comes in here, and all of these things are very brightly lit. And then this guy out here scatters rays in random directions, and a few of them contact a light surface, so it picks up a little bit of light from it. But it's random, and so maybe when you go to this guy, he doesn't hit anybody, and this guy doesn't hit anybody, and this guy hits one. And so what you end up with is a very noisy actual lighting on this world. It actually looks really garbage if you were just to do ray tracing without without any denoising on it. And so I'm trying to find the screenshot of the denoiser.
Yeah, the cool thing is when you're playing Quake 2 RTX, this is the only RTX game I know of that can do this, but you can actually turn off the denoiser and see what
cool.
the ray tracing looks like. So that's probably where that one screenshot you got came from, is just somebody turned off the denoiser.
Yeah, so with RTX on, the light, and it'll sort of bounce around. There's a GDC talk. Let's see here. See if I can find it. Well, you can see if you can find a shot of that with what the denoiser, what it looks like if the denoiser is not turned on. I watched the talk by the people that made the Quake 2 RTX, and it's really interesting. Like what troubles they had. There we go. All right. Don't copyright strike me.
I will be talking.
Okay, so. So they go through all the steps they went through to go from Quake 2 original to... There we go. Okay, here's what it looks like. Right? And so when you do the ray tracing, you're going to... What was that?
I found the actual original image that you showed.
Okay, yeah, post it on there, please. Yeah. There we go. All right. And so this is what it looks like. And it's kind of garbage, right? Like... you can see that this guy happened to just randomly hit the sky, and this black pixel next to him didn't hit anything bright, and so it's black. And so you end up with this sort of thing. And you can make it look perfect if you had infinite time, right? If you had infinite time, you can throw infinite pixels at the screen, or infinite photons at the screen, and get a perfect image. But in a game, you can't. You're limited by how many times the Quake engine, or the hardware, really, your NVIDIA graphics card can do the Bdh lookup, right? It's fast, but you're still limited. How many billions a second? I don't know. And so what they'll typically do is they'll do sort of a rough approximation. You got a light source here, so these guys are casting rays, and they're getting lit. This guy is occluded. When this guy tries bouncing a ray towards the light source, it's behind a box, so it gets occluded, but maybe it bounces up here and picks up a little bit of light, and this guy bounces over here and picks up a little bit of light, and then they average it all together, and then you get something that looks better. Let's see. Yeah, and so you can see after you run a denoising filter on it, then it actually looks pretty good. And so I'll post this talk on here. It's actually a really good talk. I really like it. So it uses data from previous frames, and averaging compensates for the noise. Yeah. Let's see. They have a bigger room. Let's see if I can find it. So let's see here. Yeah, you can see as they worked on it, it just starts looking better and better. It's really cool. There we go, this one, yeah. And so you can see that you have a couple skylights here, and so light comes in, and it's got to illuminate this entire room. You know what I mean? And so, and so this is what it looks like after, you know, you run some bounces, you know, and then you got to go from that to the indirect diffuse, and then you have that, and then specular. So diffuse is when light comes in and it kind of scatters in random directions, and specular is when you have a shiny reflection. And so they take those and sort of average them together, and so they start off. That's the noisy kind of ray tracing results, and then they denoise it, and then they combine that with the other one. Irritants channels combine, and it starts looking pretty nice, you know. And then let's see if they have the. Let's go back to the final image. And then at the end of the day, you've got God rays coming in here, and things like that. So it's really nice. My main criticism of Quake 2 RTX is actually that the world looks so nice that the monsters are completely out of place, right? Because the monsters are still from like 1997 or whatever, whenever the original game comes out, with like really cheesy animations and really cheesy sound effects. Yeah. And so it's a really awkward game to play because it's like beautiful. It's like Valheim, right? Valheim has these beautiful shaders on it, and then just like these giant, you can count the pixel kinds of things on it. Yeah. Oh, Mass Effect Legendary came out today. Has anyone played that yet? I'm kind of curious how that update went, because I don't trust BioWare very much at all these days. My daughter's asking what's Mass Effect. You know what? It means I might have to buy it for you, girl. I don't know. It's one of the best RPGs ever made. But after seeing the Warcraft 3 Reforged, it is a video game series, Ada. Yeah, Valheim's kind of grown on me, but like in this game, it's just really weird. Kind of like when I play custom TF now. FT Quake World has a fantastic renderer. It looks really nice, but you still have these like guys who have giant rectangular faces, and you know, just it's a weird combo. Yeah, Valheim. Yeah, I think their art direction's okay for the most part. In some places, I kind of wish it would make it a little bit nicer looking. Warcraft 3, Mass Effect 2 is badass. Yeah. Okay, so this talk is really interesting, and so you can see, yeah, there's the reflection, the refraction going on there, and then you cast a shadow ray here, and yeah, if you're into this kind of stuff, the main that's cool. That's good
extinction effects.
That's good look. And you have like these things that are emissive, right? So emissive textures actually radiate light themselves. So if you hit one of them with your bounce, then you pick up light from the emissive texture. You have like an emissive channel, basically. Oops, what happened here? Yeah, and so you can see the red light from this is glowing down here. It's cool. So it's a good talk. It's what 20 minutes long. It's well worth 20 minutes of your life. Okay, so come back to the original point, BVH, right? So you can represent a world using BVH trees. You can offload it onto your graphics card, and the graphics card can accelerate these things. The more of these things you cast out, the better the quality you get, the slower the performance. And so that is my TED Talk. Thank you for coming today. Thanks for a great semester, you guys. We got 15 minutes left. I'll answer any questions you guys want about video games or life or whatever. But yeah, that's basically the talk for the BDHs. Okay. Any questions about them? And you normally just let your game engine do it for you, all right? If you do Unreal Engine, you just check Enable Ray Tracing, and then it all just works magically. Yeah, if you have something to present it now. Let's do it. I'm going to need a burrito and watch you guys. I'll stop the recording now.